Hello, everyone. Today, we're diving into some profound ideas in theoretical physics: non-commutative field theory, non-commutative geometry, emergent geometry, and the quantization of space. If you enjoy theoretical physics, please like, subscribe, and share your thoughts in the comments. We'll explore today concepts from the work Novel Phenomena in Non-Commutative Field Theory, which reimagines the fabric of spacetime itself. Specifically, we're examining the idea that non-commutative geometry can be thought of as a first quantization of space, and emergent geometry as a second quantization. This two-step quantization approach redefines our understanding of spacetime, suggesting it might arise dynamically rather than being a fixed backdrop. Let's break down what this all means. But what is non-commutative field theory? To set the foundation, let's start with non-commutative field theory. In classical physics, spacetime is a continuous fabric. But in non-commutative field theory, spacetime behaves more like a quantum entity where coordinates do not commute, similar to how position and momentum work in quantum mechanics. This non-commutativity introduces two fundamental features: a Planck-like length scale where this fuzziness becomes significant, a discrete geometry that appears continuous only at large scales. These features make non-commutative field theory a fascinating approach to understanding spacetime at the smallest scales and could play a role in unifying quantum mechanics and general relativity. By treating spatial coordinates as non-commuting operators, non-commutative geometry quantizes the structure of space itself, providing a new approach for understanding spacetime at quantum scales. This is why we can think of non-commutative geometry as a kind of first quantization of geometry. First, the framework of non-commutative geometry. To explain non-commutative field theory, we need the mathematical language of non-commutative geometry. Instead of using points to define a space, non-commutative geometry relies on structures called spectral triples. A spectral triple consists of three key components. An algebra A. Think of this as defining the topology, or the shape of the space. A Laplace operator delta. This gives the geometry of the space by defining distances. A Hilbert space H. This is the space on which the algebra acts, containing the quantum states of our system. Together, these components allow us to describe geometry as something that emerges from the algebraic relations between coordinates rather than from the continuous points of classical geometry. Second, the non-commutative scalar field theory. In this framework, we can build a field theory by defining an action that combines kinetic and potential energy terms. Here's how it works. The kinetic term defines the metric aspects of the theory, essentially the shape of the space over which particles move. The potential term defines the algebraic structure, or the topology, of the non-commutative space. By constructing these action terms using matrix models, we can analyze field theories in this non-commutative context. For example, when we define a scalar field theory on a non-commutative plane or sphere, we see a richer phase structure than in commutative space, including unique phenomena like the stripe phase, a type of order that doesn't exist in ordinary spaces. Now we arrive at the idea of non-commutative geometry as first quantization. Quantization, as we know it from quantum mechanics, is the process of converting classical variables into operators that obey specific relations. Non-commutative geometry applies this idea to space itself, making space inherently quantized at a fundamental level. In non-commutative geometry, space behaves like a quantum system where we can't precisely measure both x and y coordinates simultaneously. Instead, these coordinates obey non-commutative relations, which introduces an inherent fuzziness to space. This quantized nature of space is captured in structures like Moyle-Weyl space, which uses a quantum plane, and the fuzzy sphere, a discrete version of a sphere. Thus, in traditional physics, we think of spacetime as a smooth fabric where each point has defined coordinates. But in non-commutative field theory, spacetime itself has a kind of quantum fuzziness. Here, the coordinates of space don't commute. In other words, you can't measure two coordinates precisely at the same time. This means that at very small scales, space behaves more like a matrix or grid than a smooth continuum. In simple terms, non-commutative geometry gives us tools to model spacetime at the quantum level in a way that standard models can't handle. One example is a phenomenon called UV-IR mixing. Normally, when we try to separate high-energy UV and low-energy IR physics, they stay independent, but in non-commutative spaces, they mix together. This can make things very tricky for typical renormalization techniques. To solve this, certain models, like the Gross-Wolkenhaar model, add an oscillator term that smooths out the UV-IR mixing. This adjustment keeps the theory well-behaved or renormalizable, even at the smallest scales. In summary, non-commutative geometry is our first quantization of space, giving us a base-level quantum structure that limits classical geometry's precision at very small scales. Next, we would like to reinterpret emergent geometry as second quantization. Now let's move to second quantization, which in this context refers to emergent geometry. In quantum field theory, second quantization involves quantizing the fields themselves, allowing us to describe interactions and particle numbers. Similarly, in non-commutative field theory, emergent geometry takes things further by allowing geometry itself to arise from quantum field interactions within the non-commutative space. Imagine starting with a fuzzy non-commutative space. As fields interact within this structure, they can form ordered, stable configurations where space appears smooth at large scales. This is what we call emergent geometry, geometry that arises from the interactions of quantum fields, or more precisely, the interactions of quantum matrices. So, just as fields are quantized in second quantization, geometry itself is quantized and can emerge dynamically based on the underlying quantum state. In multitrace matrix models, like those used to describe scalar fields on the fuzzy sphere, it's been found that geometry can emerge from the system itself. This is called the uniform ordered phase, where, by adjusting parameters, the model begins to display a coherent ordered geometry. Think of it like adjusting the focus on a camera lens until a blurry image suddenly sharpens. This phase change, where geometry itself seems to appear out of a more chaotic state, could offer insights into quantum gravity, where space-time geometry might emerge from quantum mechanical processes rather than being an inherent background. Now, linking first and second quantization of geometry. To put it all together, non-commutative and emergent geometry give us a two-layer approach to understanding space. First, quantization of geometry, non-commutative geometry. We start with spatial coordinates as quantized, non-commuting operators, creating a fuzzy base geometry. Second, quantization of geometry, emergent geometry. Through field interactions, geometry itself can emerge dynamically, forming coherent shapes and dimensions. This approach implies that what we see as smooth, continuous geometry might actually be a secondary property emerging from two layers of quantization happening at the quantum level. Let us now give examples of non-commutative and emergent geometries. To illustrate these ideas, let's look at two key examples of non-commutative spaces. Moyle-Weil space. This space, a flat non-commutative plane, has non-commuting coordinates that obey relations similar to the quantum position and momentum operators, i.e., the Heisenberg algebra. This space provides insights similar to those of flat spacetime and relativity, but for non-commutative theories. This is, in fact, Darboux theorem. It exemplifies first quantization by introducing a quantum structure to space itself. Fuzzy sphere. The fuzzy sphere presents another example of first quantization, but it also offers an example of second quantization. As fields or matrices interact on this quantized sphere, stable, smooth geometry appears at larger scales. This is true only at low temperatures. Indeed, the fuzzy sphere will collapse or evaporate at high temperature. This emergent structure represents a second quantization, where geometry itself isn't static, but a property that can switch on or switch off based on the quantum state. As we analyze field theories on the fuzzy sphere, we encounter new structures and transitions, suggesting that these non-commutative spaces might model quantum gravitational effects or unique phases of matter. Both examples suggest that, at quantum scales, space itself may be more like a dynamic, evolving entity rather than a fixed continuum. We come now to the first approach of quantum non-commutative geometry, emergent geometry in multitrace matrix models. In more advanced theories, like multitrace matrix models, we find even richer insights into emergent geometry. Multitrace matrix models are designed to capture the interactions of fields on non-commutative spaces. As these fields interact, they can enter a uniform ordered phase, where a coherent but smooth geometry emerges from what was originally a chaotic quantum state. By adjusting model parameters, researchers can control how this emergent geometry behaves and even estimate its properties, such as dimensions or curvature. This approach to emergent geometry in matrix models suggests that spacetime itself could be the result of quantum field interactions. As fields in these models reach certain configurations, the model enters an ordered phase where space behaves like a coherent, continuous geometry, almost as if space is switching on. The second approach of quantum noncommutative geometry is emergent geometry from Yang-Mills matrix models. So what are Yang-Mills matrix models? In the context of noncommutative geometry, Yang-Mills models provide an advanced framework where geometry can emerge or dissolve entirely, depending on the phase of the system. This takes the idea of quantized space even further, with geometry as a dynamic entity rather than a fixed stage. Let's explore how this works. Yang-Mills matrix models are a type of mathematical model used in theoretical physics to describe interactions between fields and particles in a quantized space. They are built on the principles of Yang-Mills theory, a foundational framework in gauge theory that describes how fields interact with particles. However, in the matrix model version, spacetime coordinates are represented by large matrices rather than points or continuous coordinates. These matrix coordinates can represent fields that move through a fuzzy, noncommutative geometry, with degrees of freedom that go beyond simple spatial coordinates. This setup is ideal for exploring how geometry itself can appear, change, or vanish based on quantum interactions within the matrix model. We can now explain the concept of emergent geometry from Yang-Mills matrix models. In Yang-Mills matrix models, emergent geometry is observed as a kind of phase transition. Think of it like water freezing into ice. Just as water molecules rearrange into a structured lattice at lower temperatures, Yang-Mills matrix models can transition into an ordered phase where a coherent geometry emerges. Low temperature phase, geometric phase. In this phase, the matrix coordinates organize themselves in a way that resembles a smooth geometry. For example, they can form a structure similar to a sphere or other familiar shapes. This ordered phase corresponds to what we might recognize as space with a coherent, continuous geometry. High temperature phase, matrix phase. In the high temperature or disordered phase, the matrices no longer align into any discernible geometric structure. In this phase, space effectively disappears, reducing to a purely algebraic form with no coherent geometry. This is sometimes called the matrix phase, where geometry doesn't exist in any recognizable way. This phase transition from a geometric, structured space to a disordered matrix state illustrates the concept of emergent geometry in Yang-Mills matrix models. A celebrated example of emergent geometry is the fuzzy sphere and matrix-to-sphere transition. One of the most studied examples of emergent geometry in Yang-Mills models is the fuzzy sphere. In this model, geometry is seen to emerge in the low-temperature phase. Here's how it works. At low temperatures, the degrees of freedom within the Yang-Mills matrices align in a way that the model forms something like a sphere, albeit a fuzzy one, since it still has quantum properties at small scales. As the temperature increases, however, this ordered sphere structure begins to dissolve, eventually transitioning into the high-temperature phase where the spherical geometry disappears, leaving only matrix entries with no specific spatial structure. This matrix-to-sphere phase transition exemplifies how geometry can appear and vanish in response to changes in the Yang-Mills matrix model's state. What are the implications for quantum gravity? Thinking of geometry in terms of first and second quantization offers new insights for quantum gravity. Here are some of them. Quantum gravity, without a fixed spacetime. If geometry emerges from quantum interactions, we may not need a fixed spacetime background for describing gravity. Geometry as a dynamic phase. Unlike in classical physics, where geometry is a fixed background, Yang-Mills matrix models suggests that geometry itself could be a phase, changing in response to system conditions. Spacetime as an emergent phenomenon. This approach implies that spacetime might not be fundamental, but could emerge from a more basic matrix structure at quantum scales. Gravity, then, could be understood as a property that arises only in the low temperature or geometric phase of these matrix models. Reconciling quantum mechanics and relativity. Traditionally, quantum mechanics and general relativity clash when applied to spacetime. However, if spacetime itself is emergent, general relativity could be an approximation of a more fundamental quantum structure. Spontaneous symmetry breaking. Noncommutative field theory introduces unique mechanisms for symmetry breaking, a critical process in particle physics. New phases of matter. The complex phase structures in these theories might model exotic states of matter or describe transitions in high-energy environments like those found in the early universe. New insights for high-energy physics and early universe models. This layered quantization provides a way to describe the universe's structure during high-energy conditions, such as those in the early universe. Spacetime geometry might have solidified from a highly noncommutative or emergent state as the universe expanded and cooled. Insights into early universe physics. Just as phase transitions shape matter in our familiar universe, the early universe might have undergone similar transitions in its geometry, moving from a disordered matrix state into an ordered, geometric spacetime as it cooled. To wrap up, we explored the layered nature of quantizing geometry. Noncommutative geometry acts as a first quantization, providing a quantized base for space, while emergent geometry serves as a second quantization, where geometry itself becomes a dynamic, emergent property. This perspective may redefine our understanding of quantum gravity, quantum fields, and the fabric of reality itself. Thanks for watching and exploring the quantum nature of space. If you enjoyed this journey through noncommutative geometry, please like, subscribe, and share your thoughts in the comments. Until next time, keep questioning, keep exploring, and keep seeking out the hidden layers of the universe.